Hello, in this video we're going to be talking about finding maxima and minima using the first derivative. So let's talk about what we mean by absolute and local extrema of a function f of x. Absolute extrema are the highest and lowest values of a function over its domain. Local extrema are the highest and lowest values of a function within smaller open intervals contained in its domain. And you can have multiple local extrema. Local extrema can also be the absolute extrema, but local extrema cannot be the endpoints. When we talk about having a local extreme value, it's got to have some graph on both sides of it to be classified as a local extreme value. So that's why we wouldn't have this endpoint or this endpoint classified as local extreme values, because there's no graph on one side of these endpoints. So let's look at this graph here and see what we mean by absolute extreme values. So we can see that this is the lowest value of all for this entire graph, and we would call that the absolute minimum. This right here is the highest value for this entire graph, so this would be your absolute maximum. So now we've got several peaks and valleys here within this domain from left to right endpoints. So we call these your local maxes, so local max, local min, local max, local min. This right here is an inflection point, so it's neither a local max or a local min. So let's look at a few graphs. So the graph of this upward facing parabola has an absolute minimum, but it does not have an absolute maximum, because no matter how high we are, we can always go slightly higher, so we can't say there is one value that is an absolute highest value. This graph here has asymptotic behavior, where you can see the left and right ends are approaching a horizontal asymptote, y is equal to 0. We can see that it has an absolute maximum value, but no matter how low you go on either side of this graph, you're never going to be able to say that you hit the lowest value, because you're going to keep approaching y is equal to 0, but never actually arrive at one value that we say is at the lowest value. So therefore this graph would not have an absolute minimum value. So taking a look at this graph, so this is either a sine wave or a cosine wave. It has periodic behavior. So we can see that it reaches its highest value in multiple places, and in fact in infinitely many places you can reach the absolute maximum value of 1, and in infinitely many places you can reach the absolute minimum value of -1. So this illustrates that you can have an absolute maximum and an absolute minimum value occurring in multiple places within the domain of the function. This graph right here has no absolute maximum and no absolute minimum, because you can always go lower and lower, and you can continue to find a lower value, so you will never arrive at the smallest value. And that can be said for the maximum value too. You're never going to arrive at the maximum value, because you can always find another one that's even higher. And this is an inflection point here at 0, so that's neither a max or a min. In this graph here, this is a closed interval between 0 and 4, and you could tell by the fact that these dots are filled in here. So you can see that this dot right here, 0, 2, this one, is the absolute highest value. We would classify that as the absolute maximum. However, if I go down to this empty circle here, I can't classify that as an absolute minimum value on this graph, because you're approaching -2 in the y, but you never actually arrive there. You can continue to get closer and closer to -2, so you don't have a certain particular value that we can claim is the absolute minimum value. So we say this graph has no absolute minimum value. Now I look at this graph here. This is also over a closed interval, but I can see that this one does have an absolute maximum, and this value right here, this 0.20, is the absolute minimum value of this graph. So this graph has both an absolute maximum and an absolute minimum. So taking a look at this graph here, it has a vertical asymptote as at x is equal to 2. We could say our domain is square bracket 0 to 2 with a round bracket, meaning the graph is approaching 2, but 2 is not in the domain of this function. So if I look for an absolute minimum value, I can see that I do have an absolute minimum value here, but I don't have an absolute maximum value because this end of the graph approaches positive infinity as x approaches 2, so I'm never going to be actually reaching a certain value that we can classify as the maximum value. So this one only has an absolute minimum. If I look at this graph over here, this is a closed interval between these two endpoints here. So I can see that I have a lowest value here at this leftmost endpoint and a highest value here at this cusp. So this y value at the cusp would be my absolute maximum, and this y value at the leftmost endpoint would be my absolute minimum value. You can also see that you've got a local max and a local min here too. So next we talk about critical values. Critical values are the values within the domain of the function where the first derivative is either 0 or the first derivative does not exist. So these x values are called critical values. Critical values indicate the possibility of local extrema occurring at these x values, but they don't guarantee that these x values are local extrema. When you set the first derivative equal to 0 and solve for x, it's possible you may get complex solutions. For instance, if you were solving quadratic formula to find x and you ended up with a negative under the radical. So when this happens, we ignore these complex x values because we're only interested in real values that can be plotted on the xy plane. So if I look at this graph once again, I'm going to have f prime equal to 0 at this point because I'll have a horizontal tangent line. Same can be said for this point here. And at a cusp, the first derivative would be undefined. So you can see that this is a local max, this is a local min, and this here is a local max. So Fermat's theorem addresses the critical values where the value of the first derivative is 0. So the theorem says that if f prime of c exists and f of c is a local extrema, then the first derivative must be 0. So what that means is that if the first derivative is 0, you have a critical value at that c value in the function. If this is a local max or a local min, then you conclude that you must have had a horizontal tangent line. Basically, that's what it's saying. The converse of Fermat's theorem, however, is not true. If the first derivative at a value is equal to 0, you may not have a local max or a local min because there's also the possibility that you have an inflection point. So basically, having the first derivative equal to 0 is a necessary condition to have a local max or a local min, but is not a sufficient condition to conclude that you have a local max or a local min at that x value because you very well could have an inflection point instead. So the other type of critical points are those where the first derivative does not exist. So you could still have a local extreme value at these C values, at these critical values, and these situations could be one of these three here. So you could have a cusp. So this would be where f prime is undefined. So it could be pointing upwards or pointing down. Those could be local maxes or local mins. You could have a corner. So f prime is undefined at a corner. So those could be local maxes or local mins. And then the other possibility is that you could have a vertical tangent line, and f primacy is undefined at vertical tangent lines, and those would be neither local maxes nor local mins. So this slide covers the critical points where the first derivative is undefined. So one last theorem to cover here. This is called the extreme value theorem. The extreme value theorem applies for functions that are continuous over a closed interval AB. So f of x will have an absolute minimum and an absolute maximum somewhere within that interval. The extreme values will occur at either the endpoints or the critical values within that closed interval. So we find the value of the function at all critical values and the value of the function at the endpoints, and we compare these values and determine the highest and the lowest values. The highest will be the absolute maximum, and the lowest will be the absolute minimum. If I look at this graph as an example, my closed interval is between A and B. My value of the function at the left endpoint is f of A. The value of the function at the right endpoint is f of B. And then I have two critical values in the interior. So this critical value can be classified as a local max, and this one here as a local min. When it comes to absolute maxes and absolute mins, this endpoint would be the absolute minimum, and this interior point here, which was a local max, could also be classified as the absolute maximum. And this endpoint over here would be neither. So example 1 here says find the critical points and classify these as local extrema, absolute extrema, or neither. So step 1 would be to find the first derivative and locate the critical values. So we have 4x minus 12. We set that equal to 0. So we have 4x is equal to 12, or x is equal to 3. So we have one critical value. So since f prime of c is equal to 0 at x is equal to 3, we could either have an inflection point or a local max or a local min. And those local maxes and mins could also be classified as absolute depending on what your function looks like. So what we do know is that this function, this quadratic, is facing upward. So this shape is what we have. So we are going to have an absolute minimum value here of this quadratic. And so what we found is the x value where this occurs. So now if we want the value of the absolute min, we would plug 3 into the function and find out, if I run that through my calculator or do it in my head, whichever, is that your y value is negative 4. So this point 3, negative 4 is my absolute minimum. Example 2 says find the critical points and classify the critical points as local extrema, absolute extrema, or neither. So notice that we're given a polynomial and a closed interval. So the extreme value theorem applies to this problem here. this is a continuous function over a closed interval. So the extreme value theorem says we're guaranteed to have an absolute maximum value and an absolute minimum value on the interval. So the procedure is we first find the first derivative. So that would equal to 2 times negative 1/2. So that's negative x plus 1 equals 0. So that means x is equal to 1 is my critical value. I have one critical value. So according to the extreme value theorem, I have to investigate my two endpoints and my critical value. So I'm going to make a little table, an XY table, so I can compare these values. So I'm going to go in order from lowest to highest, negative 2, then 1, then 2. And if I plug those x values into my function, I'm going to get y values 1.5, 6, and 5.5. So then I look at these values and I classify them according to absolute minimum. So the lowest value is the top one. This will be my absolute minimum. The highest value is the second one. This would be my absolute maximum. So I know that this is, let's just see what this looks like. I know that this is a downward facing parabola. So it's got the point negative 2, 1.5, rough sketch, 1, 6, and 2, 5.5. So over the closed interval, I've got these 3 points that I'm investigating. The leftmost and rightmost endpoints and the critical value, which is the absolute maximum value since this is a downward facing parabola. So I have this horizontal tangent line, or f prime is equal to 0 right here. That's my absolute maximum value. So this is what my graph looks like, and we've solved this using the extreme value theorem. So example 3 says, find the critical points and classify the critical points as local or absolute extrema or neither. So I have a x-cubed polynomial on a closed interval, so I can apply the extreme value theorem. So first I want to find the critical values. So that means f prime of x is equal to 3x squared minus 16x plus 20. Set that equal to 0. So I want to check and see if I can factor this. If not, I will use the quadratic formula to find the x values, which are the solutions to f prime of x is equal to 0. So 3 times 20 is 60. So I can say 6 and 10, negative, negative. So this is factorable. So 3x squared minus 6x minus 10x plus 20 equals 0. 3x, x minus 2, 10, x minus 2 equals 0. X minus 2, 3x minus 10 equals 0. Set each factor equal to 0 and solve for x. X equals 2. X equals 10 over 3. So these are my critical values. Now, according to the extreme value theorem, I'm going to evaluate the endpoints and the critical values and find the value of the function there and decide which one is the lowest and which one is the highest. So I'm going to make a little chart. So my left endpoint is 1, and then I'm going to go in order, 2, then 10/3, and then my right endpoint is 5. I'm going to sub those values into my function to get my y value. I'm going to write those down. And then I'm going to find the lowest value, which will be my absolute minimum. So that's the first value here. This will be my absolute minimum. And the highest value will be my absolute maximum. So that would be this value here. And then I'm going to classify those two interior values. So those two had derivative values equal to 0, so they will have horizontal tangent lines. So if I take a look at this x cubed polynomial, so that's going to go n behaviors such as this, so down, up. So I'm just going to make a really rough sketch here just to get an idea of what's going on. So I've got the point 1, negative 5. I'm going to say that's here. 2, negative 2. Let's say that's here. 10/3, negative 3, so roughly here. And then 5, 7, so let's say that's here. All right, so on my left end, I'm down end behavior. And my right end, I'm up end behavior. So connecting the dots, I'm going to have to turn around here and here to get this end behavior. So here you would see that I'm going to have a local max and here a local min. So that means at x is equal to 2, I'm going to have a local max where I turn around and a local min at 10/3 where I turn around again. So that takes care of classifying each of these endpoints and critical values. So we finished this problem. And we had to draw on our knowledge of end behavior in order to make a determination about what was going on the inside of this function with the local max and the local min. Example 4 says find the critical points and classify the critical points as local extrema, absolute extrema, or neither. So I have a x to the 5th polynomial with a negative leading coefficient, and this is not a closed interval. So we're going to find the first derivative. So f prime of x is negative 60 x to the 4th plus 300 x cubed plus 120 x squared. And I'm going to set that equal to 0 to find my critical values. So I'm going to divide by negative 60. So I get x to the 4th minus 5x cubed minus 2x squared is equal to 0. I'm going to factor out a x squared. So I'll have x squared minus 5x minus 2 is equal to 0. So that means this will be true if x is equal to 0. That'd be one of my solutions to this derivative equation. Now I can't factor that quadratic factor, so I'm going to have to use quadratic formula to find the critical values for this quadratic factor. So I have negative 5 plus or minus the square root of negative 5 squared minus 4ac divided by 2a. So I'll have 5 plus or minus the square root of 25 plus 8, that's 33, divided by 2. So that's going to give me two decimal values, real numbers, and those will be 5.3723 and negative 0.3723. So I've got three critical values for f of x, and I want to classify these. So I'm going to make a table, and I'm going to put these x values in order from lowest to highest. .3723. I'm going to substitute these x values into my polynomial, and I'm going to get y values, negative 2.5 0.5374, negative 2, and some very large positive number. This is an x to the fifth polynomial, so you can get very large numbers in a hurry. All right, so now I want to classify these according to what I know about the graph. So let's take a look at the graph and see what's going on with these critical points on my graph. So we said this was a x to the fifth function polynomial with a negative leading coefficient. So end behavior on such a function would be up, down, negative x to the fifth function. So rough sketch, just to get an idea of how to classify these values here. I've got a negative, that would be my first point. Let's put it here. And then a 0, negative, I'm going up slightly to here. And then I've got 5.37 and some very large value. Let's just put it here just to get an idea of what's going on. So if I put in my end behavior, I'd have to be going up and then down. All right, and then in the middle, I'm going to have to turn around here to hit this point, but that is not going to be a local min or max. Otherwise, I'd create another valley, which I know I don't have. So I'm going to continue going up like that. So this is an inflection point here. And I know it's not a local min or a local max, and I know that because I've only got 3 places here that could potentially be local mins or local maxes. So I know I've got to turn around here to hit that dot, and I know I had to turn around here to hit that dot. But if I turn around here, then I'm going to have to turn around again down here, and that would be a fourth critical value, which I know I don't have. So that's why I'm certain that this has got to be an inflection point here. Otherwise, I'll create another turn in the graph, which I know is not there because I've only got 1, 2, 3 critical values. The left one I had to turn to hit this one, and this one has to turn to go back down here. But if I turned here and went down again, I'd have 1, 2, and that'd be 1, 2, 3, 4, and I know I've only got 3. So this has to be an inflection point here. All right, so now, since that's an inflection point, I can classify this one as a local max. So that's this here. And I'm classifying it as a local max because I could see that I'm still able to hit positive infinity over there. So there's going to be higher values than that. And I'm going to classify this one as a local min. And by the same reasoning, this has an arrowhead, so I know there's going to be much lower values that I can reach. So this is a local min in this localized region. All right, but it's not the absolute min, nor is this the absolute max. So this point 0, negative 2 was an inflection point, so that's not any extreme value. So we're just going to say neither here. All right, so we've classified all of the critical values as extrema or neither. Inflection points are neither. So example 5 says find the local extrema of the function here. So we can see we have an x in the denominator, so this is a rational function. It's not a polynomial. So we got to take the first derivative to find our critical values. So first let's write this as powers. Then we'll take the first derivative. So this is 2x minus 2 divided by x squared. We'll set that equal to 0 and solve that. So we'll have 2x is equal to 2 over x squared. So that's 2x cubed is equal to 2, x cubed is equal to 1, or x is equal to 1. So we have a critical value here. Only one critical value for this function. All right, so we want to figure out how to classify that critical value there. All right, so let's figure out what the y value is first of all. So we need f of 1. So that would mean 1 squared plus 2 over 1. 1 plus 2 is 3. So we have the point 1, 3. All right, so let's see what's going on with the graph of this function here. This is a rational function with only one critical value. All right, so let's try to figure out what's going on with this function here. So the function is x squared plus 2 over x. So let's get this into one fraction. So this is x cubed plus 2 divided by x. All right, so I can get the zeros from the numerator. So when x cubed is equal to negative 2, and I take the cube root of negative 2, I'll have my only zero. I've only got one zero. The cubed root of negative 2. And then so this is a 0. So let's say that's here. Then I've got a vertical asymptote. X is equal to 0, so let's make a dotted line for that. So I know that. And then I've got the point 1, 3, so let's say that's here. And I know that. So when you've got a vertical asymptote, you're either going to approach going this way or this way, and the same thing here, you're going to either approach going this way or this way. So we need a few points so we can just make a rough sketch here. So let's go over here and make a little rough sketch, a little table. So we've got the point 1, 3. So if we get close to the vertical asymptote over here, let's say we got point 1, that'll give us an idea of whether we're going to go this way or this way. So this point right here, being a critical value, is either going to be a local min, a local max, or a inflection point. So let's figure out what that is. So like I said, if I get close to that vertical asymptote approaching from the right, I'm going to choose a value of 0.1, and I sub that into my function, and I get 20. All right, so that answers my question. It's going up here. All right, now let's try on the other side of x is equal to 1. How about 2? Let's try 2. When you plug in 2, is it going down here or is it going up here? So when I put in 2, I get 5. So it's going this way. So that means I've got right here a local min. So this is a local minimum. All right, and why do I say it's a local minimum? I say it's a local minimum because there's another piece of this function. Now, we want to be able to decide whether to classify that point there as an absolute minimum or a local minimum. Well, I can already see that this point is lower than this point here, this 0 over here, but there's some behavior going on over here. It might be good to know what's going on. So if I approach this asymptote here from the other side, so let's say I'm at -1. Let's put that value in here. If I'm at -1, I plug that into my function, I get -1. So I'm down here. So this function is going down here. So clearly there are going to be lower values than that dot, which I classified as my local min. All right, it's not going to be the absolute min. But this problem just said to classify, no, it said find the local extrema. All right, so I've got the local min there. Now, I checked a few more dots over here. This guy, this graph is actually going to head up this way somewhere over here. All right, so I'm going to classify my one critical value as a local min, and I'm going to conclude that there's no absolute minimum or absolute maximum value because of these arrowheads here on this piece of it over here and this piece of it over here. All right, so you're not going to be able to reach one value that we can classify as the absolute minimum value or the absolute maximum value. Okay, so there's only one local minimum for this function. Example 6 says find and classify the extrema of the function. So I have another rational function, but this time it's on a closed interval. So we need to evaluate the endpoints and the critical values. So let's find the critical values by taking the first derivative. Using the quotient rule, I've got the bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. And I'm going to set that equal to 0. So in order to figure out what x values cause this function to equal 0, I'm going to set the numerator equal to 0. So let's distribute. Remember, the only way to get this value, this rational function here, which is the function that the first derivative is now, is to find out what x values cause the numerator to go to 0. So 50x squared. So this is minus 25x squared is equal to minus 625, which means x squared must be 25, which means x must be plus or minus 5. So these are my critical values. Right now, I'm going to make a table with my critical values and my endpoints and make some decisions about extreme values. So I put them in order. Now I'm going to sub those into my f of x, and I'll get my y values. I write them down. And then I'm going to make a decision. So the lowest value here, according to the extreme value theorem, I'm guaranteed to have an absolute min and an absolute max if I have a continuous function over a closed interval. Right, I know this is a continuous function because there's no vertical asymptotes in this rational function because x squared plus 25 will never be 0. All right, so this is definitely a continuous function here, continuous rational function. So lowest is the second value here, so I'm going to classify this as my absolute minimum. Highest is this one here. This is your absolute maximum value. And these other two are endpoints. So endpoints cannot be locals, cannot be local extrema, so we will classify these as neither. Okay? So what this function looks like is this kind of a symmetric function about the origin. We found these two local extrema here. Absolute extrema, I should say. This is the highest value, and this is the lowest value of this function. All right? Example 7. Find the absolute extrema of this function. Once again, we have a closed interval. So these are continuous functions. The e to the x function will be continuous over this interval. So we can go ahead and find the critical values, taking the first derivative. Let's do that first. So the derivative of e to the negative 3x would be e to the negative 3x times negative 3 using the chain rule, minus e to the negative 5x times negative 5, that would become positive using the chain rule. All right, so I can say that 3e to the negative 3x equals 5e to the negative 5x. All right, let's get the e's over on one side. So let's get the 5 over here. So I've got 3/5 e to the negative 3x equals e to the negative 5x. And let's get this e over to this side here. 3/5 is equal to e to the minus 5x minus negative 3x, using what I know about simplifying expressions containing exponents. So what I did there, I know that if I have, let's say, e to the 5 divided by e to the 2, that's the same thing as having e to the 5 minus 2, which is equal to e to the 3, because when we divide, we subtract exponents, just like as if those were x to the 5th divided by x squared. Same idea. So now I've got that's equal to e to the negative 5x plus 3x, e to the negative 2x. All right, so now to solve that, I would take the natural log. Let's just put this together of both sides to undo the e, so I can get the x out of there. All right, so that undoes the e. So then that means that x must be equal to the natural log of 3/5 divided by negative 2. So that's going to be a decimal number. So if I type that into my calculator, I get a critical value of 0.2554. All right, so I've got one critical value for this function, and I've got the two endpoints. So I'm now going to make a chart and decide which are the absolute extrema. So I've got in order negative 1.145, then 0.2554, and then 2.255. Subbing those into my function, I'm going to get y values, and then I'm going to compare. These are my y values, subbing into the function. So we're guaranteed that one of these is your absolute minimum. So that would be the first one, according to the extreme value theorem. And the second one is the highest, so this is going to be my absolute max. And the last one is an endpoint, so this would be no kind of, so we say neither, no kind of extreme value if it's not an absolute. It could never be a local. All right, so we've solved this. We've got our absolute min and our absolute max. Okay, so this time we have a trig function over a closed interval, so we're guaranteed if this is continuous, which it is. Trig functions are continuous. Well, sine functions are continuous. I'm guaranteed to have an absolute max and an absolute min. So we're going to find our critical values first. So first derivative, 2 minus 8 times the cosine of theta. Set that equal to 0 and solve for theta. So 8 cosine of theta is 2, equals 2. Cosine of theta is 1/4. Let's just say 0.25. So that means theta would be the inverse cosine of 0.25. So I would type that into my calculator. All right, let's work in radians. This is 3.14 radians. All right, so theta, the inverse cosine of 0.25, typing that in, I get 1.25 3181 radians. All right, so now I make a chart with my three values. So this is my critical value. So I've got my first endpoint, 0. Then I've got my critical value. Let's change that to theta and f of theta. 3181. And then my right endpoint, which was pi. Now I'm going to sub those into f of theta, and I get 0, negative 5.1097, and 2 pi, or 6.28 radians. Okay, now I'm going to decide which is the lowest, and that would be my absolute minimum. So this is the lowest, so this is my absolute minimum, which is the highest, so that would be this one, the last one, would be my absolute maximum. And then this is an endpoint here, so it can't be a local extreme value, and it wasn't an absolute min or max, so this one be neither. All right, so I've solved this one for the absolute extrema of the function. Last example here. So this is one of our old familiar problems, but we're going to talk about this in terms of our new vocabulary and procedures in this section. So we have an object that's thrown into the air, and its position is given by this quadratic equation. Find the time at which the object reaches a maximum height, and find that maximum height. So first thing we do on these kind of problems is find the first derivative and set it equal to 0. So h prime of t, so 2 times negative 7.6 is negative 15.2. That would be t, plus 62 is equal to 0. So t is equal to 62 divided by 15.2 seconds, 4.0789 seconds. So this is my critical value. So I know that since my first derivative is 0 at this value, and I know that this is an upside down parabola, that could only mean that we're talking about this point right here, because this is the only place on an upside down quadratic which would have a first derivative or a horizontal tangent line. First derivative equal to 0, I'm saying. So what I found there is this max time here corresponding to the maximum height. So T max, which is the time of maximum height, is 4.0789 seconds. H of 4.0789 would be, if I substitute that into h of t, I get 141.447 meters. All right, so that's my maximum height and my time at which that maximum height occurs. All right, so this is a familiar problem, but in terms of what we know now in this unit, this is basically your absolute max, or it could be considered a local max over a so that takes care of our problem set here. You should have enough information now to try the homework set, and let me know if you have any questions about the homework set. You should have enough information to get started on those problems.